A very warm welcome to all of you. Myself Rajan Choudhary, Professor in the Department of Civil Engineering, Indian Institute of Technology, Guwahati, instructor for the NPTEL MOOC course Pavement Construction and Technology, funded by Ministry of Education, Government of India. Today's talk will be in continuation to our previous talk, which is on mixed design of bituminous bound courses under the module 4 of this particular course. In the very beginning, I would like to acknowledge the use of text, information, graphs and images sourced from various textbooks, codal standards, journal articles, reports, newsletters and public domain searches. In the last lecture, we discussed about the different phases of a bituminous mix when it is compacted using aggregates and binder. Now, there we discussed about the different volumetric parameters which are here. You can see the volumetric parameters are this is a three-phase diagram. This is your air which is there, this is the binder which is there, which is free, and this is that small amount of binder which can be absorbed by your aggregates, and then the remaining is the aggregate volume. So, this is shown in this particular manner. This volume of the aggregate is the bulk volume of the aggregate, so it can be mentioned at VSB also and VS whichever manner. And then this is the volume of bitumen, which is you are having the free bitumen. This is the volume of air which we have. This volume of free bitumen plus volume of air is your voids in mineral aggregates. We discussed this particular one yesterday, and this forms your total volume of your mix. And if we talk in terms of weight, then the volume corresponding to this VSB will be your weight of the aggregates for this entire free as well as the absorbed bitumen. We have to work out the weight, and that will be WB of the bitumen. So, WS plus WV will be your total weight of the mix, where you do not include the weight of the air, considering as it is negligible. Now, let us consider an example to see how the shears can be. So, for an example, the total volume, this is just an example to explain the things in a simpler manner, not what the determinations or the figures which are shown here are realistic picture, but this is to make the things easily understood. So, if a total volume of a compacted specimen is 100 cc. So, this has been made as a 100 cc, so that we can make the other computation simple. Volume of air, if one can figure out, so what is here this total volume of this particular specimen, which we determined through water displacement method, which we discussed in the previous lecture. So, that the GMB, when we measured the GMB, where the weight of the mix is there and the bulk volume of the mix is there. So, the specific gravity corresponding to this particular one, from this, if we get since weight is known to us, the bulk density will be determined through this water displacement method. I can get the volume of the specimen. So, here I have taken an arbitrary number, so that let the volume of the specimen is 100 cc, out of which the volume of the air is 5 cc. To explain what VMA means, what VFB means, what air void contents, all this exercise, what percentage of binder absorbed means, what effective binder content means, all this I am trying to explain through this simple example. So, if the volume of the air which is present in this 100 cc of volume of a compacted specimen, which is mentioned here 5 cc. Now, volume of effective, that is the free bitumen. If the free bitumen is say 10 cc in this particular one. So, this VFB or VBF or VBE, which is your 10 cc in this particular example. Volume of mineral aggregates corresponding to its effective specific gravity. So, there we discussed in the previous lecture, if there is a air void, there is an aggregate, there may be some surface voids may be there. So, a part of it may be filled with your binder gets absorbed on the surface. So, remaining voids, which are these are the remaining voids, this plus this volume will be your effective volume. So, it does not includes the voids which gets filled with the water. So, that is what is your GSE effective specific gravity. And if you recall, yesterday we discussed as expression where it is the percentage of mix minus the percentage of bitumen and percentage of mix divided by your maximum specific gravity which we worked out, and this is the percentage of binder by weight of mix, percentage of binder by weight of mix, this is the specific gravity of bitumen, and this is the maximum specific gravity which we determined through the your rise specific gravity meter or through vacuum sealing method. So, if that is known, then we get this value of GSE. So, corresponding as weight of aggregates is known, correspondingly you can work out the volume. So, this is the specific the volume which is shown here is the one which includes the solid part plus the volume of solid part plus the volume of voids which are not filled with the bitumen. So, this is mentioned here as 84 cc. Binder absorbed in the aggregates is 1 cc. So, this much binder absorption is there, 1 cc gets absorbed. So, if this 1 cc is this volume, so 1 cc plus what you have here is 84 cc, this is 84 cc. So, this 1 cc is the volume of bitumen getting absorbed and 84 cc is the remaining volume of your aggregates. So, this 84 plus 1, it is not plus 1 is 85, which is your bulk volume of the aggregates. Now, assuming a specific gravity of binder as 1, so and it is mentioned that assume the specific gravity of binder as 1 and bulk specific gravity of the aggregate blend as 2.5. Now, with this particular one, we will try to attempt this exercise. Now, first of all, we are trying to look for the voids in mineral aggregates. Now, if you recall, voids in mineral aggregates which we mentioned yesterday was volume of bitumen which is free or volume of bitumen which is effective plus volume of air divided by the volume of the mix. Now, into 100 as it is to be expressed in percentage. Now, what is there? Volume of free bitumen, here is it is the effective binder which is, so that particular one is 10. What is the volume of air? Which is 5 cc, total volume is 100. So, this will be giving you 15% of your VMA. Now, so voids in mineral aggregates in a compacted specimen is 15%. What is the air void content? Air void content is the volume of air divided by the total volume of the specimen. So, it is 5%. So, this is how there we got air void content as GMM minus GMB upon GMM into 100. I am just trying to explain what it means. Now, in addition to this one, the other part was how much voids gets filled with the bitumen. So, we were having the binder which is free. Here we will consider only binder which is free, which is either VBE or VBF in whichever manner you mention. This is volume of bitumen which is effective for coating or volume of bitumen which is free for coating. So, that was 10 cc and VMA was your 15. So, into 100, so this comes out to be 66.6%. So, this is what you have for your VFB. Now, here it comes bitumen content by weight of total mix. Now, I have to figure it out. So, for that particular one, total binder is how much? 1 cc is absorbed in the aggregate, 10 is free. So, total volume is 11 cc and considering a specific gravity of 1, I am taking the weight of binder as 11. So, this particular one, so my total weight of will be 10 plus 1 will be my total weight of binder considering specific gravity 1. Now, weight of aggregate in the specimen, the specific gravity, bulk specific gravity was given as 2.5 and what was the bulk volume of the aggregates? It was the effective volume plus 1 cc was the absorbed bitumen. So, the in the previous slide we mentioned that VSB is your 85 cc. So, considering this 85 cc and this bulk specific gravity, this will be the weight of your aggregates. Now, 212. So, what will be the percentage of bitumen? PB. PB will be the weight of the bitumen divided by weight of aggregate plus weight of bitumen into 100, because here we have to consider the weight of the mix. So, for that particular one, the weight of aggregates is 12 212.5 and the weight of the binder from here 11 gram. So, this is total is 223.5 gram. So, this percentage of binder will be 11 divided by 223.5. So, it is 11 divided by 223.5, 4.92 percentage by weight of binder we are having in this specimen. Now, if one asks that what is the binder with respect to or the binder which is getting absorbed in the aggregates. So, that is PBA, because it is with respect to the weight of binder which is absorbed upon weight of aggregates, because this percentage is with respect to the aggregates. So, here binder absorbed is 1 and the weight of the aggregates is 1212. So, this comes out to be, so the binder which is getting absorbed in aggregates is 0.47%. So, this gives an idea what we are doing there. And then there was another term PBE, how much is the effective binder which is available, and this is with respect to the mix. So, here this should be weight of binder which is free upon weight of mix into 100. So, that particular one, considering the 10 gram was the free, so specific gravity of 1, so 10 cc was free, specific gravity 1, 10 gram is the free binder, and this is the total weight of the mix 223.5. So, the binder which is effective is 4.47. So, this is PBE. Now, because of the absorption of the binder, the initial binder content which was 4.92 is effectively 4.47 only, because a part of it is getting absorbed into the aggregates. So, this explains the volumetric computations which are to be done during these bituminous mix design, or understood to be understood during the volumetric mix design. Now, once the volumetric parameters are determined, like your maximum specific gravity, bulk density, the specific gravity of the aggregates, and the compacted specimen density, the other parameter which is to be determined is the stability of that particular mix, especially because the method which we use for design of bituminous mixes is known as Marshall method of mix design. And this method was first developed in 1939 by Bruce Marshall of the Mississippi Highway Department, and this get further refined or modified, especially during the Second World War. The US Army Corps of Engineers modified the equipment and procedures, especially for use in during the World War, for use in the design of airfield pavements. And then with in due course of time, continuous extensive laboratory and field studies have been done, and this method have been modified, and presently widespread acceptation of this particular one is there for design of bituminous mixes for use in flexible pavement construction. The two important key steps involved in this Marshall method of mix design is evaluation of paving bitumen, the binder which is to be used, evaluation of aggregates to be used, that we discussed in our previous lectures about how the binders, different binders are to be evaluated, how aggregates need to be evaluated for use in a particular bituminous bound course. And then the second one is fabrication and evaluation of Marshall mix specimens for determining optimum binder content. Now, here it says that once you fabricate this compacted specimen, then your exercise should focus on determining optimum binder content, the binder content which is the best one. This should not be too high, this should not be too low. As I said, too low may also have a concern, and too high, one common concern is the cost will increase. So, and other concerns may be regarding the performance. So, you need to work out the one which gives you the, it's an optimum one which gives you the desirable performance. Now, for this particular exercise, the cylindrical specimens were which are to be prepared. The most commonly used are 4-inch specimens having a diameter of 101.6. This is specifically for aggregates having NMS up to 1 inch, and for NMS greater than this particular one, normally for NMS up to 37.5 mm, that is 1.5 inch, we can normally go for specimens prepared with a diameter of around 6 inches. And that particular method, when this the mix design method, when modified especially for 6-inch specimens, that is known as modified Marshall method of mix design, and the one which is practiced with 4-inch specimens is the standard Marshall method of mix design. There are certain differences which are there, especially like the hammer weight is there, the mold sizes are there, and then the requirements which are to be there on the parameters which are obtained out of it. So, now during the fabrication, one important aspect, so it says the selection of the binder and aggregates, and then fabrication, and thereafter determination of optimum binder content. Now, during the fabrication, certain things are to be taken care. One important parameter is at what temperatures the aggregate and binder are going to be blended. Now, because we need to heat the aggregates, we need to heat the binder, but at what temperatures it need to be heated, so that we can get a good coating over it. So, we need to determine the mixing and compaction temperatures. In many cases, the agency which provides the binders, specifically the modified binders, on the basis of their experience during the development of their binders, they recommend, okay, for these binders it is preferable to use these mixing and compaction temperatures. For most of the paving grade binders, an extensive research have been done, and for paving binders it is suggested that if you are using a paving grade binder to produce bituminous mixes, then the two viscosities which are recommended for mixing and compaction temperatures are, it says that the mixing temperature should be the one which gives a viscosity in the range of 170 plus minus 20 centistokes. So, and the compaction temperature should be the one which have a binder viscosity in the range of 280 plus minus 30 centistokes. So, for this one, now we need to have information available with us over the variation in the viscosity of a paving grade binder with temperature. So, here you can see this is a plot which is there, where the temperatures are shown. This is a log plot which shows that there is a temperature and there is a viscosity. So, we need to plot the relationship between the viscosity and the temperature, and from that relationship we need to work out the temperatures where the binder have a viscosity in this particular range. So, here you can see this is the range, this is the range, this is the range of temperature where your mixing viscosities are met out, and this is the range of the temperature where your compaction viscosities are met out. So, you, as there is a range of viscosity, you will have a range of temperature. So, in that range of temperature you will heat your binders up, and aggregates are usually heated to 10 to 15 degrees centigrades higher than your binder, because binder is more susceptible, it gets highly oxidized when subjected to higher temperatures. So, aggregates are slightly kept at a higher temperature. So, we mix them at mixing temperatures, and then finally they are compacted at the temperatures which corresponds to this viscosity of 280 plus minus 20 centistokes. Now, once the mix is prepared at this particular temperature corresponding to this one, the mix is stored in oven for a period of 2 hours. This is for conditioning, and that is done at the compaction temperatures. So, what compaction temperature we are going to use to produce those cylindrical specimens, we will condition that specimen at those temperatures for 2 hours. This helps us to simulate the short term aging which can happen with this mix when it will be produced at a hot mix plant, because there it will be produced, it may be stored for a period of time, then transferred to the field and finally layered and compacted. So, it remains at that higher temperature for a good period of time. So, to simulate how much aging happens, how much binder absorption happens into the aggregates, this conditioning is done, and thereafter we do the compaction of these ones by pouring these loose mixes into these cylindrical molds and giving the standard blows as specified by, we follow the Asphalt Institute manual series also. IRC 111 also gives us the method for working out. ASTM guidelines are also there, IS guidelines are also there to conduct this Marshall method of mix design. So, then the blows are applied, and this compactive effort which is applied on, we pour the loose mix in these cylindrical molds and compact it by giving blows on both the sides. Now, this compactive effort have to be good enough to produce the density which will be there in the mix after 2 to 3 years of service life. So, this is an important aspect, that the compactive effort which needs to be selected at the laboratory scale as per Marshall method of mix design, which is followed. It recommends for 75 number of blows on both the faces of the specimen. So, one face is given, and when the NMS is higher, when we go for 6 inches of specimens, it states that for 6 inches dia specimens we go for 112 number of blows on both the faces. And once this compaction is done, then we go for the density void analysis, and second is the Marshall stability and flow determination to work out the optimum binder content. So, this is all pics shown in a systematic manner. You have your binder, you have fine filler, you have fine aggregates, coarse aggregates. The batching is to be done. You need to combine all those aggregates. Aggregates are heated to the mixing temperature, then poured to the mixing bowl. Binder which has been brought to the mixing temperature is added, and whatever trial binder content you may start, depending upon what mix you are targeting. The initial trial binder content may be, say, one binder content may be 5%, and you may have to do various trials. We normally go with an increment of around 0.5%. So, I may go up to 7.5%. So, I may do these at 5, 5.5, 6, 6.5 and 7 or 7.5%. So, normally we go for at least 4 to 5 trial binder contents to get the optimum binder content. So, I'll first pour the binder corresponding to one trial binder content, and then it will be mixed. Then we are conditioning it in oven, then brought to at the compaction temperatures, and then are compacted, and here you get your specimens. Now, all these specimens are compacted specimen, and I have shown here. This is how the nomenclature can be given. Say for 4.5, for each binder content I will at least prepare 3 replicates. So, here you can see for 4.5 3 replicates, 5, 5.5, 6, 6.5. So, here 5 different binder content, trial binder contents, and in addition to this particular one, you have to prepare loose mix for the determination of your maximum specific gravity. So, if a mix design is to be attempted where 3-4 different aggregate stockpiles are there, and you normally work out for 4 to 5 trial binder contents, and each at least 3 specimens at each binder content, and then 3 specimens, 3 to 4 specimens may be required for your loose mix, especially the maximum specific gravity determination. It can be done at all binder contents also, or it can be done at a binder content which can be more closer to your optimum binder content. So, then 3 to 4 specimens may be required there. So, in total you may require to prepare around 18 to 20 specimen batches, loose mix batches, out of which around 15 to this particular 15 to 16 will be compacted, and remaining in loose mix for determination of your maximum specific gravity. So, for this particular one, usually you may require for one mix design around 25 kg of aggregates and 4 liter of binder. Now, once the specimens are compacted, volumetric parameters are determined, then we work out the determination of Marshall stability. This we discussed in one of our previous lectures also, when characterization of bituminous mixes was there. So, this is tested to determine the Marshall stability and flow. This gives us a measurement of the strength of the mix, especially resistance to plastic flow of compacted specimens. They are to be first brought at the test temperature, which is 60 degree. For that they are kept in a water bath for 30 minutes. Then they are transferred to this Marshall stability mold. There the load is applied. The load is applied at a rate of 2 inches per minute, and simultaneously the deformation is measured, flow is measured. So, you have the load measurement setup, and you have the displacement, the deformation measurement setup is there, and maximum load is reached, and then the load starts getting decreased. So, you are not we are going to note down the maximum load which is taken by the specimen, and corresponding flow or deformation which has taken place in the specimen. So, the stability is the maximum load, and corresponding the amount of deformation is the flow. These two are to be recorded from this particular test. Once this is done, so volumetric parameters are determined, stability and flow is determined, we plot these properties with respect to the binder content. So, what we will plot the specific gravity or bulk density, or it is also referred as unit weight of the compacted specimens with respect to the bitumen content. The second one is bitumen content versus Marshall stability. Third one, because we have chosen say 4 to 5 trial binder contents, bitumen content versus flow, bitumen content versus air voids, bitumen content versus VMA, voids in mineral aggregates, and bitumen content versus voids filled with bitumen. So, these 4 parameters we got from the volumetric measurements, and along with this 5th parameter, which is the density measurement, and this is what we got from the the 4 parameters which we got is the 1, 2 and 3 and 4 are we got from the volumetric measurements, and the flow and this one we got from the stability and flow measurement. So, these stability and flow are also to be plotted with bitumen content, and the other 4 volumetric parameters are to be plotted, so as to see the trend how these parameters are varying with the change in the bitumen content. And finally, we need to target what should be the our air voids, what should be VMA, what should be VFB, flow, because all requirements. Now, this is a table as per IRC 111 2009, which says that if a viscosity grade binder is used, where as per Marshall method 75 number of blows are given, the stability should be at least 9 kilonewton. At a temperature of 60 degrees centigrade, it says that the flow in mm should be in the range of 2 to 4. So, I need a binder content which should meet out these requirements. There is another parameter, Marshall quotient, which is the ratio of your Marshall stability and flow, which says should be in the range of 2 to 5. Percentage air void should be in the range of 3 to 5%, and it says that the voids filled with the bitumen should be in the range of 65 to 75%, and thereafter for voids filled in mineral aggregates also it says depending upon the NMS of that particular mix and the air void content target. Since the air void here is 3 to 5, if my target is 4%. So, I will look for this 4%, and my mix may be for an NMS of 13.2. So, in that case my minimum VMA requirement will be 14. So, I will do this design considering. Now, here I have already fixed out what is the requirement of flow, say as per this table for a viscosity grade binder, it should be in the range of 2 to 4, air void should be in the range of 3 to 5, the bitumen content versus VMA, it should be more than 14%, VFB, it should be in the range of 65 to 75%, and there is no as such requirement of bulk density. It is just to see the trend how density is varying with the bitumen content, and Marshall stability is it should be greater than 9 kilonewton. So, I need to pick up a binder content which meets out all these requirements which are stated for a particular mix. Now, it is for modified bitumen also there are certain requirements is given which are slightly different to what we have for viscosity grade binder. Now, this is when the standard Marshall method of mix design is used. When you are using a modified Marshall method of mix design, the stability requirements and flow requirements are to be multiplied by 2.25 and 1.5. So, whatever stability 9 kilonewton will be raised to a figure of 9.9 kilonewton into 2.25, and what is the flow which is there from 2 to 4 will then it becomes here 3 to 6, because it is to be multiplied by 1.5. So, this is because when the specimens you are making for 6 inch specimens. Now, in most of the cases we prefer, IRC 111 also says that air void content is a very important factor to control the performance of bituminous mixes. So, always target for achieving 4% air void contents, and then see at that trial binder content whether you are able to achieve the remaining parameters. If you are able to achieve at that binder content which is giving 4% air voids other parameters, then that can be taken as your optimum binder content. Now, so what we get out of it, we need to balance out. We need to balance out specifically that all parameters are met out at our binder content, and it may happen that for the trial binder content, which is for target 4% air void content, some of the parameters may not be able to meet out. In that case, you have to do some changes, especially that changes are done with respect to the change in the aggregate blend, especially mainly we do in terms of the aggregate blend. So, here I have this VMA, because VMA says that we should have a VMA which should be more than that particular figure. So, any VMA, so I will see this shaded part is there where I need to have the binders where it is meeting the requirement. So, there in this particular range my VMA is meeting a requirement, VFA 65 to 75%, I am plotting my asphalt content, and I just want to see where my requirements are not met out. So, VMA here it says it is too high, the voids filled with the vitamin, air void and stability. So, in that case what may happen, finally you may have a small range of binder content in which all criteria are passing. Within this particular one, there was always one prefer to have a lower binder content, because if a range of binder content is available for you, say if this may be to say from 5.2 to 5.5, now one may prefer to go for the lowest one. In addition to this particular one, with the current guidelines and the recommendations, it states go for a binder content which gives you 4%. So, whatever binder content which gives you 4% of your air void content, see whether it meets the other requirement. If it meets the other requirement, that can be considered as your optimum binder content. So, this slide shows the 6 different plots which are drawn between the bitumen content. The first one is unit width, bulk density, second is an air void content, third one Marshall stability, fourth voids filled with the asphalt or bitumen, fifth flow, and your sixth is voids in the mineral aggregates. And for different mixes, as we will have different requirements in terms of the voids in mineral aggregates, like here we can see this is the requirement for voids filled with the bitumen. The air void requirement is 3 to 5%, the Marshall stability requirement is minimum 9 Kn is there, then Marshall flow requirement is from 2 to 4, and a ratio of Marshall stability and flow is also given as a Marshall quotient, that requirement is mentioned here. Now, for the VMA, depending upon the NMS of the aggregates in that particular gradation and the air void content which we are targeting. So, as mentioned previously, many a times we target for the design air void content of 4%. So, if I look for an NMS of 13.2 for 4% of air void content, I will require minimum 14 VMA percentage. So, one way I can do with this particular one, I will just try to look where I get a target air void content of 4%. So, from my plots I will see this particular one, and then I will look into it. It may be somewhere, this particular one may be somewhere around say 6.75 or 6.7. Now, for that 6.7 percentage of my binder content, which is corresponding to 4% of air void content, I will look for the other parameters. I will see what is the Marshall stability, specifically the Marshall stability in this case may be a value which may be around 2725 in that particular case. Here I will check for the flow, what is the range of flow which is given here, and I will see what is the VMA requirement, I will see what is the VFA requirement. If it meets my requirement, I can accept this particular binder content and I can consider it as my optimum binder content. If it does not works out, then I will have to make some changes in my aggregate gradation. So, an example has been created here where this is a bituminous mix design. Marshall specimens are prepared at 5 different binder contents using a paving grade VG30 binder, and the bulk specific gravity, what information is given, that the bulk specific gravity of the combined aggregate blend was determined as 2.674. The specific gravity of binder is 1.03. Then as I mentioned, we can determine the maximum specific gravity at a particular binder content, which may be quite close to your optimum binder content, because this comes with the experience with the different kind of mixes. So 5% was selected, and there the GMM was determined at laboratory scale. Once that GMM was determined, GSE was obtained using this GMM, and then this GSE was kept constant, considering it that there will be not appreciable change or significant change, which this is aggregate specific property. So not much change is expected. So GSE, which is derived from 5% binder content having this GMM value, was then kept considered for the other binder contents also, and then using this GSE all these GMM values were determined. Simultaneously, the other parameters VA, VMA, VFB, Marshall stability, flow and quotient, those were determined. So here it is mentioned that GMM, this was measured in the laboratory at 5%, and then the GSE was computed, and from later on all other GMM values were derived using this GSE. So a plot is drawn using those values. Some of the plots are shown here. This is the plot of the air void content, Marshall stability, VFB and the Marshall flow. The VMA plot is there. So in addition to this, you will have the density plot also, because you need to know what density will be achieved at optimum binder content also. So if I am targeting for 4% air void content, I will look for this particular one, and there may be a binder content which may have a value somewhere around 4.66. Now for this, if my target is for air void content 4%, I got this binder content as, and I'll now need to check whether all other requirements are meeting it or not. So this is my Marshall flow value which I got. This is my Marshall stability corresponding to this particular one. This is my voids filled with the bitumen. This is my VMA. I ensured it with my requirements here. This, so for this particular one, my air void content is 4%. The range required was 3 to 5. When I checked for the Marshall stability, it is 10.34, higher than the requirement of 9 kilonewton. When it is for Marshall flow, it is 3.16, requirement is 2 to 4 mm. When it is for voids filled with the bitumen, it came out to be 71, around 71%, requirement is 65. And when VMA, it came out to be 13.83 and requirement is 13%. So then I can consider this 4.66 as my optimum binder content, and I need to get from the plot between the density and the binder content, my density of the mix to which it is to be compacted in the field. So this becomes my now optimum binder content. This is a conventional method of mix design which is attempted for bituminous mixes, and as I said, we discussed earlier, bituminous bond mixes are of different types. We have the one which are used for wearing courses, which we can use for binder courses, which we can use for base courses. So, and for wearing courses also we have different kind of mixes. We have bituminous concrete mix, we have the stone matrix asphalt. This is one kind of mix which we discussed earlier. This is a gap graded mix. A particular size is getting reduced so as to bring more contact between the coarser aggregate particles. And SMA is a mix, stone matrix asphalt is a mix which is getting quite popular, specifically because of its high rut resistance, aging resistance and its high durability. So especially nowadays for flexible pavements having design traffic more than 50 MSA, it is always recommended to use SMA as a wearing course. And while compacting this particular one, the guidelines which are to be followed is IRC SP 79 2023, and there are certain, because now here you will have fine aggregate proportion a bit less, filler is quite high, and then a coarse aggregate skeleton is there. So it looks, a stone matrix skeleton looks in this manner compared to what we have the conventional dense graded bituminous concrete mixes. So here you can see the proportion of larger aggregate particles, coarser particles are more, to bring more contacts between larger aggregate particles for a better load dispersion and a greater strength. And since the voids are going to be filled up with the mastic, which is your fines are normally 8 to 12% of filler is used in this case, and the binder which is also required is a bit higher for the stone matrix asphalt because a high amount of filler is there. So it fills the interstices, and this forms a matrix which is strong enough to take the traffic loads. Now since there is a good amount of fines and a slightly higher binder content, chances are there that when these mixed are produced at high temperatures, especially when mixed and produced and compacted, this binder may move down in your loose mix because under gravity. So this phenomenon is normally known as drain down, where the binder moves within the mix under gravity. So there will be a variation in the amount of binder content. The top of the mix may have lower one, and there may be excessive binder content in the bottom part. So this variation is not good for the performance, and it needs to be controlled. For that particular purpose, fibers are very commonly used for stabilizing it, so as to control this drain down feature. And if you see the requirements, here also the requirements are very similar. It directly says go for 4% air void content for determination of your optimum binder content, and it says minimum starts at 5.8%. Then cellulose fibers, this is one type of fiber for stabilizing additives. Voids in mineral aggregates are to be quite high enough, so that it says 17 as a minimum value, so that you can accommodate more amount of your specifically the binder in this particular one. So voids in, and then there is a voids in coarse aggregate which is there. Asphalt binder drain down, as I mentioned, this is the drain down. A test is done to ensure that the movement of binder under gravity is within a limited value only. So that is 0.3%. I will just show you in the next slide. This tensile strength ratio, which we determined the indirect tensile strength of conditioned and unconditioned sample. Conditioned was subjected to freezing and thawing, and unconditioned was not subjected, and both the samples then brought to a temperature of 25 degrees centigrade. This we discussed in one of our previous talks, and there says that this ratio should have at least a minimum value of 85. The preferred one is 90%, and the same TSR strength ratio in case of bituminous concrete or other dense graded mixes is 80%. So here you want to be a more durable. This is more durable, the requirement is higher. Now this is how a skeleton looks like, and there is one test which is usually done to ensure that good contact points exist between your coarse aggregate particles, and that we call in terms of stone to stone contact. So in stone matrix asphalt, it is important to ensure that there is a good contact between the coarse aggregate particles, and for this one a test which is done where first only the coarse aggregates are dry compacted, and the voids in those dry compacted aggregates are checked in coarse aggregates, and we call that particular one voids in coarse aggregate under dry roded condition. It is filled in layers by giving tamping, and the volume of this cylindrical measure is known, the weight of the aggregate is known, specific gravity is known. So I can work out the volume which will be there in this compacted aggregates in this particular cylindrical mode. So this gives me my VCA DRC, which is voids in coarse aggregates in dry roded condition, because there is no binder, only aggregates are there. So this is for coarse aggregate. Now I will add the binder to it, and I will prepare a mix. So when I prepare a mix, I can work out what is the percentage of fine. I will work out what is the percentage of fine which is there, asphalt which is there, and the air which is there. If this percentage is less than this voids in dry roded condition, then I can expect a good amount of stone to stone contact, and this is what is ensured in this particular specimen. It says that voids in coarse aggregate of your mix should be the voids less than in your dry roded condition. So this helps us to ensure a good stone to stone contact in SMA mixes. And this is the simple representation of the your binder drain down test, where you prepare a mix, and this is subjected to this wire mesh basket, and it is kept in an oven. So, the prepared mix, whatever binder which is lost through this particular sieve is collected down, and we see that this should not be more than 0.3%. So, the binder drain down is restricted, and this is the IS 18104. So, this is to ensure that there is no loss of binder during the production and construction especially. So, this binder drain down test is done. Similarly, one more mix which is popular is OGFC. This is quite popular in many countries, specifically because of its abilities which are regarding to a quick drainage which is there, high skid resistance, and the low tire pavement interaction noise are there. These mixes are designed at a higher air void content. What we considered for SMA and the bituminous concrete other dense graded mixes, we were targeting to 4% air void content. Here we are targeting to 18 to 25% air void content. So, this is important. Now, so the compaction process is different. There usually in SMA we give the compaction through Marshall hammer of around 50 number of blows on both the faces. So, the compactive effort needs to be changed when you are working out with different mixes. So, and when these mixes are designed at these higher air void contents specifically to allow water to flow within these mixes, and they are in most of the cases they are not considered as structural layers, they are considered as a drainage layer of thickness 1 to 2 inches, and the water flows within them. They are constructed over existing dense graded surface. So, that water does not enter in the below layers, it travels within that layer and moves out from the edges. So, here again the requirements are in terms of cellulose fiber, the binder content, the air void content in the range as per IS 129 in the range of 18 to 20%, 18 to 22 VMA. This is again the voids in coarse aggregate in the mix, which has to be less than, so as to ensure a good stone to stone contact. Now, the other mix which is there in this particular category is gap graded rubberized bitumen mix which is there. This is again where you are using the rubberized bitumen or the bitumen which is modified through the use of waste tire rubber. So, that is the guidelines for gap graded wearing coarse mixes with rubberized bitumen or bitumen rubber. Here again you go for a binder contents which are slightly higher. It says that we will go for binder the bitumen binder percentage at least 7% is the minimum one, and there the requirement of Marshall stability is comparatively less for this one, especially for gap graded mixes, and then the voids requirement. So, they are designed in more or the same manners, but their requirements which are to be met out, the differences may be in terms of the parameters which is to be checked and the compactive effort which is to be applied. So, and the trial binder contents, because based on the experience we can know that SMA mixes will generally require higher binder content. So, we can start from in our trials at a slightly higher binder content compared to what we do for bituminous concrete mixes. And there in most of the mixes presently we target the air void content and then try to see whether other parameters are getting are met out at our that particular binder content. If they are able to meet out, we will call that binder content as optimum binder content. So, this is all about the design of different kind of bituminous mixes. Thank you.